All right, good afternoon, everyone. We're going to go ahead and get started. I would like to welcome everyone to BIOMES. So BIOMES is YSE's flagship seminar series on many different various topics in environmental science. My name is Brandon Lewis. I'm a PhD student in YSE and also a member of the BIOMES committee. And we have a great speaker for you today. So I'll introduce her, and then she'll come up and do her thing. So Anna Dyson, Dr. Anna Dyson, is the Hines Professor of Architecture at the Yale Schools of Architecture and Environment. She is the founding director of the Yale Center for Ecosystems in Architecture, a research initiative that integrates interdisciplinary labs across campus to collaborate on the research, development, and deployment of novel architectural systems that are focused on the challenge of metabolizing energy, water, and materials within architecture in radically new ways. Dyson has been directing design research programs that have competitively won awards and contracts from multiple sponsors such as the National Science Foundation, the U.S. Department of Energy, the Environmental Protection Agency, the United Nations Environmentalist Program, and also from private sponsors such as the Bill and Melinda Gates Foundation. She's the recipient of the Innovator Award from Architectural Records. Dyson holds many international patents on building systems, innovations for the collection and distribution of clean energy, water, air quality, and material life cycles. So I would like to go ahead and welcome Dr. Anna Dyson. Please have me welcome.
Okay, can everybody hear me? Yes. I think it's on. Okay. Thanks so much, Brandon, and to the other students for the invitation here. It's really exciting to speak here. My first time speaking actually at the YSE. And I realized that I'm also an appointment. My appointment covers the YSE, and we have a lot of collaborators from the YSE, both students and faculty. So I'm very excited to be here. The title of this talk, I oscillated between two different titles. One, Fear of Ecology, or Ecology of Fear, and Built Ecologies. And I ultimately settled on Built Ecologies because our field is commonly known as the built environment. And we talk about the built environment process. But the built environment process historically has been focused around the needs of human beings and has typically taken mechanical and electrical and throughput material paradigms to achieve the ends of human beings in the built environment. And therefore, the sort of ethos or the drivers for how we build, why we build, where we build are very human-centric. And starting with transitioning built environment, which could even actually and often does leave humans out of the equation, and human comfort and health and well-being, which is inextricably linked to extended ecosystems. I proposed several years ago in the first PhD program that I founded and built at the Center for Architecture, Science, and Ecology in New York City to transition the name Built Environment to Built Ecologies. Okay, there we are. And today I'm just going to touch on a few of the concepts of what we do. This is just a gift from our website, so please go onto our website if you're interested further in the way that we drive research, which is basically through large-scale projects. we constantly label what we're doing according to different categories that the world expects: energy, air, water quality, material life cycle. But in reality, if we're going to deliver environmental systems or building systems for cities, then we don't have the luxury to focus on any one of those things. So the way that we look at research is typically going to be through the lens of ecosystems. So how does water interface with, say, energy and materials and food and life cycle? And so we'll talk a lot about whole life cycle today and what whole life cycle means for the future of the built ecologies and cities and buildings. I would definitely love to invite you guys. We're going to be hopefully launching our space in New Haven. A lot of our work up to date, we're a relatively new center, only a few years old, but we've been doing most of our work off campus in New York City, in Arizona, in Guatemala, South Africa, Nairobi, only because that's where we've been working. Those are areas where we've been working for a long time, and the pandemic kind of delayed our center, but hopefully you'll be able to visit us on Howe Street, because we're going to have our sort of all under one roof lab, the YSE lab on Howe Street in New Haven, and we're super excited about it. And what do we do essentially in our labs? What we do is we cross-link the work of a lot of different labs: living systems labs, engineering in electrical, mechanical, systems integration, integrated systems. And we relate those experiments, correlate those experiments to large-scale deployments in built environments, in buildings like this. And our goal really is to accelerate the innovation and the sort of radical disruptive innovation of ecosystems and architecture. And why is that so critical to kind of go back and forth between the lab? Well, typically within a lot of labs, we're looking at things in a very, very focused and, in a sense, narrow way, right? We tend to want to limit the variables. We tend to want to examine the system in a very focused way. And what happens, as I've said, in built environment is, if you just look at things from one perspective, you will lose so much information about how it will end up behaving in the life cycle. So our role is really as integrators across scales and across systems, across different areas of inquiry. Just a note about what planet do we think we're living on? I think we will all look at this image differently. I think we all understand our environment and our the context within which we're working very, very differently. But one of the things that will characterize the built environment process, so BEP, that's what it's sort of classically called, is that we are also, in a sense, constantly working within a context that's already built. And we are also considering now that even in the most so-called, let's say, wild, removed condition in the middle of a forest or in the middle of a field far away from any type of urban development or human habitation, we would still consider that an urban process, because in our context, we're now sort of responsible for all of those interdependencies across scales and across time. So this is a view of the globe at night from NASA. We could look at it in so many different ways. For example, today we can see the wholesale propagation across continents of solid state lighting, for example. There's a very recent innovation only from, really we've only seen that blow up in the last 20 years in terms of wholesale adoption. But, and that was hailed as an incredibly energy efficient sort of revolution in lighting. This building, for example, even with all of the daylighting attempts that we have here, we can see the lights are on. They don't need to be on. We can turn them off, please. Ask to turn them off, but we really don't need them. But prior to LED lighting, commercial buildings such as this would have had 40% of their energy consumption profile on the maintenance of lighting loads. That's a huge, huge number. And now all of a sudden it's reduced to a fraction. However, many of you in this room might know that LED lighting is possibly catastrophic for the circadian rhythms or the diurnal sort of cycles of local flora and fauna and human beings, by the way. So we don't actually, so you can see that when we look at things just from a vantage point, energy savings or efficiency or material efficiencies or other things, without necessarily considering literally how does that technology integrate at small and large scales, we could see the propagation of systems that really are not, in a sense, supportive ecosystemically. So this is just one example of why we feel it's so important to look at integrated systems over time, and sometimes over geological timescales, very, very large timescales, because as we'll see here in global cities, a lot of our global cities are starting to look more and more alike, right? With the sort of propagation, again, of mineral-based building methods like concrete and steel, and powered by fossil fuels on the inside for heating and cooling. But in reality, all of these cities are extremely different because they are interfacing with completely different micro and macro climates across their length and over time. So completely different condition. And one of our biggest questions is, how can we reconsider cities in order to be in sync with living systems in the context in both the most local sense, in the regional sense, and also in the global sense. And then also, how could we potentially consider our cities as is, because most of what we see today in 80 years will be still there. I think it's 80%, sorry, by 2050 will be what we see in front of us. So we have to, in built up economies. So we really have to think in our own context, you know, about how to completely reconceive the building stock we already have. You know, it's tempting to see these situations as very, very different. We have a settlement on the left-hand side of Manhattan that is obviously completely different in scale and scope, but they do share one thing, as we can see from the smoke coming up, is that increasingly at that time, the people living there would be burning things to maintain their life, cooking, thermal comfort, et cetera, and to make things. And on the right-hand side, we are also using that. We might not see the bonfire, we might not consider it, but we burn in order to run this city to the tune of over 11,000 megawatts per day. And then to make things, it's also tempting to look at all of our emerging technologies, the very advanced technologies such as nano and bioresponsive technologies and all the things that we think might be very green. But the truth is that the more we go down in scale to manipulate our materials in order to deliver, let's say, heating, plug loads, cooling, computers, all of these things, we have more and more embodied energy. In fact, just for the chips in all of our systems, we have to control heat past heat flux past 1,000 degrees C and back within just a few seconds in order to form these materials. So we're embedding more and more and more embodied energy into our materials and our systems. What does this mean for how we respond to where we're at in time right now for built ecologies? Just as a few global figures that might not be well known by everybody, is that already in 2020, we're at 37% or over 37%, way over by some estimations, but this is a conservative estimation that neatly considers the embodied and operational energy of buildings, embodied meaning everything we use to extract, transport, make, implement. And we can see that in 2021 here, the operational energy is almost 75%, right, of the built environment. So we've as a society, been working really, really hard to try and reduce the operational loads of buildings. There's many ways that we can do that, both by cleaning up the grid, supplying it with renewables, but also by designing our buildings to be energy efficient. This building here could be extremely energy efficient if, if it were tweaked, if the original intentions of the buildings evolved, and if there was a proper maintenance of the intentions of how this building would run, which is not true today. Like for example, if anybody finds it a little stuffy in here, even me, far away from you, I can feel the CO2 rising in here. I don't know if everybody else can, but you will definitely by the end of my lecture. This room was designed to have operable windows, and we could have a very nice fresh air and a very nice cool condition that where the majority of people might be comfortable. That's a tough thing because obviously everybody has a different thermostat, right, in terms of what they prefer, both culturally and biophysically. But the truth is that this was perfectly designed for cross ventilation, for both very nice air quality and for thermal. That is not the way the building is being used. So that's one of the reasons why looking at the relationship between embodied energies, the way a building was designed, how it gets operated, how it is dismantled, is absolutely critical to consider in sync. And so what is whole building life cycle? Well, typically when we looked at the built environment process, we would count the building life cycle as from the extraction of materials, all the, you know, the impacts of the extraction, let's say the production, the transport, manufacturing, on-site construction is a big one. And then in this particular diagram, you can see what's in gray are the maintenance loads, which are actually outsized, as we saw, in comparison to all of those other things. But increasingly what we have to do with whole building life cycle is we absolutely have to consider the environmental impacts of choices, right? How we literally even just move soil around a site in order to put a building like this. Think about what we had to do to this site to put this building in. And all of the different choices that we make in terms of the procurement of materials. What is that doing to regional, global, and local ecosystems? There are tremendous impacts. And in fact, the work of the built environment process does not start with us. It starts with the work of the geobiosphere. And that's why we need to, in a sense, we're starting to now think about these things in very, very expansive timeframes with the consideration of non-renewable resources that took very extended timeframes to produce. And that is true even for locally earth-based materials. Anything that we procure or we extract or we move will have consequences, in some cases, catastrophic. So, and who's involved in this process? So typically also what would happen in the built environment process is it would almost be a linear condition where designers and demolition companies, et cetera, had very little to do with producers. You might look up tables and say how much embodied carbon is in this material or that, but as we all know, the data surrounding all of these decisions is really in progress, let's say. A lot of it, the provenance of that data, the semantics of the data, where, you know, who's responsible for it, how trustable is it, really has to be questioned at every step, and it becomes extremely complex. Think once again, just even of this room, how many complex systems that are coming from all over the world. These materials are coming all over the world, just even within one device. So the supply chains are very, very complex, and the decision-making process is also very complex. However, in this diagram, the decision-making process tends to get set in the design phase very early on in the design phase, and it is constrained, highly constrained by policy, by finance, and by the context, the socioeconomic context. So there's going to be some real challenges towards getting the right decisions unless all those different stakeholders are aligned. So that diagram was meant to say that in order to effectuate a whole building life cycle, we have to have a different alignment and different lines of communication across stakeholders in time, and also, of course, the popcorn trail of who's made the decisions for what reasons and be in discourse. And as I said before, when we're looking at New York City, for just as an example, but this is zooming out to global, we can see that the majority of the materials that we build with today are mineral-based, right? We've got massive quantities now of concrete, steel, brick, and aluminum. And in this graph, we're looking at a projection over time that is even with best practices of today. So we can see that there's unfortunately a serious problem here with what it is that we're doing and how we're building it in terms of the impacts on environment, ecology, and carbon. But I think it's really worth stating that it hasn't always been that way. And, you know, our recent past, even the last 200 years, is very, very short. Here we look at a graph that only looks at the recent past of since the last, the Second World War. So we're looking at less than a century. And what do we see here? These are global material flows, including all of the flows. So that includes agriculture, for example, or other things. We can see that mineral-based processes were a tiny fraction of our global material flows. And that includes, by the way, global cities, such as this one here. This is actually a picture of Dubai. And for those of you that might be going to COP28, I thought I'd put that up because I know that the School of the Environment is very involved in these events. The Dubai of today is barely recognizable from the Dubai of the mid-20th century. But all over very large, dense cities, such as we're talking London and Paris. And just to put this into perspective, Paris has a larger per square mile density than New York City. So it is a dense city. And even in the interior structures of London and Paris, Berlin, large cities, you would have seen bio-based materials as the primary structure, not concrete and steel, as many think. So we're talking about the global construction boom that we're about to enter from here to 2050. There's an anticipation by the United Nations Environment Program that we will be adding a city the size of Paris, that means the floor area, the size of Paris, every 5 days to our globe. So it's a massive amount of construction. Simultaneously, as we know, we can see down in the 2015, we do have a lot of biomass, and a lot of that biomass is going to waste. It's being burnt, or it's being dumped, and it becomes biohazards in local economies where it's being generated, in agricultural economies. So we do have a tremendous opportunity for two things that I'll talk about. Is the more we build, the more material we have in the built environment. So that's a really important concept, because if we start designing for circularity, if we start considering our buildings as material banks and not as sort of throughput, you know, things that get built up, get demolished, get dumped. But if we start really designing for disassembly and reassembly, right, we can actually see some of that in this room today. We can see these panels and many other systems could very easily be repurposed, reused, and that would be the highest value. If we had to dismantle this building, we would want to reuse components without having to recycle, right? We don't want to put more energy and more chemistry and more things into the process. We'd like to actually just keep things intact, and that goes for whole buildings. But if we did have to build new buildings, we have tremendous material flows in the biomass sector. And what we're talking about really, maybe in a transition to circular material economies that are bio-based, is not necessarily the forestry or heavy extractive economies that we are familiar with. There are some countries that claim to, like my own country, I'm from Canada, and to claim to have sustainable forestry. I think obviously that's an expanded definition, and I don't mean to come to the School of Forestry to say what sustainable forestry is. When I started, it was called the School of Forestry. So the School of the Environment, I will leave that to the experts, but I think everyone in the room can agree that the future extraction of biomass and materials, whether they're timber-based, post-agricultural byproducts, bamboo, or other biomass forest detritus, will not look the way that our methods look today, that there's going to be a tremendous revolution in the way that we work with ecosystems in order to extract materials. However, we do need to start to think about, and you can see today here on the left-hand side, we see all the preponderance of renewables here, right? We've got almost 90% of renewables. with the bio base is very, very small. We're recycling or reusing very, very little. You might stop me and say, well, aluminum or steel, these are eminently recyclable. Don't we recycle 90% of steel in many economies? This is true, but the problem is with the global construction boom that I just mentioned, there's a growing gap between the availability and the supply of recycled or reused components. So that's why we start to see that increasing. So these are projections that we are making, we are proposing with colleagues at the School of Forestry and others, School of the Environment. And the idea is, how do we get to, by 2060, to on the right-hand side, where we start to see that the preponderance of our materials might be reused. We might have a circular material economy. And if we do need to extract, maybe we will extract the same amount of forestry right now, but we will do it with, for example, very sustainable methods. And we will be very, very careful about the way in which we decarbonize our conventional materials, such as concrete and steel, in order to minimize their impacts moving forward. So let's go back to our city just down the road. Looking at it from another standpoint, so that's sort of just an overview, very, very quick snapshot of what we mean by life cycle and whole building life cycle in the built environment. But what are we actually doing when we're building? We can see here from this picture, but in a way it might be less obvious sitting in this building, but even in this building, are we building with nature-based processes, and are we letting nature in? Or do we tend to be very, very careful about controlling and pushing nature out of our built environment process and how we run the built environment? As I said, this room in this building had a lot of very interesting and different and new ideas about how to do that. But a building has to evolve, right? It has to constantly be adjusted by its owners and occupiers, who are us. And it has to be in dialogue or discourse with the time. Right now, we have if we look at the condition here, we could almost see the left-hand side of this image as a kind of Brownsfield site for both humans, flora, and fauna, because we know, as we find out on the terrain of genome sequencing and so many things that are blowing up in terms of understanding the impact of our environments on human beings, that the fact that we spend over 95%, for example, in the Northeast of our time indoors, this is a very, very low biodiversity environment, even the one we're sitting in right now. It'd be a lot better if we opened the windows, but us sitting right here, what we're doing is we're sharing human microbiome, right? We're not interfacing. We evolved over time to share our environment with extended living species, but we are sequestering ourselves and cutting ourselves off, right, from the flora and fauna that we co-evolved with. So that has huge implications. It has implications for inflammatory illnesses and all sorts of what we would call developed economy or first world problems. That we have health and well-being problems that are related to a really low biodiverse environment. And so what we do, as I said, is we investigate the interrelationship between all of these issues, the issues of how we relate to the environment in terms of the procurement and deployment of systems. How do we maintain them for our own health and well-being? And historically, we've worked with a lot of, I'm going to show you a few very, very large commercial building projects, and I'll show you a few complexes that are built from scratch. But before we do that, I'd like to just introduce one of our ongoing projects where we decided to partner. We were actually asked to partner, I have to say, with UNEP and others on a program called Ecological Living Network, where we would investigate literally the interrelationship between all of these ecosystem factors and human beings in a very small housing module and in different climates. So as we said, we would never build the same, even in, this is in New York City, but we would never build the same in New York City or anywhere else. There's no two site that would be alike. And there's no two family or individual or group that would be alike either. Sorry, I don't know why that's not working. But so this is not meant to be a prototype for export or a prototype for saying this is how you do it. I want to be really clear about that. That's not what it is. It's an investigation. In this case, it's meant to house a family of 4 with only 100, roughly 20 square meters or 200 square feet. So it's a very, very small. And why do we take that dimension? Is because that is the dimension that the UN High Commission for Refugees has for a family of 4. That's an allotment of space. So the idea was to understand exactly how much could we sustain in terms of security just on site. So what is that interface between people and the site? We're not designing this for the UNHCC. That's not it. What we're doing is trying to understand what is the interface between humans and their environment in terms of requirements and in terms of what can be procured right on site. So obviously there's a lot of data that we have to acquire. We're both acquiring environmental and data off of how both living systems with plants and humans are doing in that environment. To build this, and you'll see in Nairobi, for example, we would never build with timber, but it just so happens in this case, we made the decision to build with timber from the Northeast. When I say Northeast in quotation marks, a lot of it did come from Quebec, but just really kind of bean counting, the environment around the system and really understanding what are the impacts of all the decisions. So for example, one of the most important thing we need for sustenance as we mentioned, in an environment is air. That's what we're really delivering first when we think about our built environment. Nobody can survive without proper air quality. So how do you survive with air quality, for example, in environments like New York City or other environments when the exterior air quality is extremely compromised? And in many informal conditions, especially in migrant conditions or refugee conditions, is open air. So you have a really, really difficult time. You have to oftentimes burn biofuels in order to cook food, and you're subject to very, very low standards in terms of emissions from vehicles and manufacturing and other things. So this is where the ecological living network is kind of an open architecture for, it's not privileging one technology or another. It's not privileging one group or one university. It's basically inviting a lot of plug and play or testing of different strategies in order to do certain things. In this case, we're testing the ability of a bioremediation wall to both remediate water and on-site water collection and air quality through the root rhizosphere and through the plants. This is a very temporary and not a very sophisticated sort of wonder closet that we put in the back just to as backup for this particular one, but just to look at the amount of space that you would have for all your environmental control systems. It's a very, very small amount. Oh, on the waterfront too, we were, we invited colleagues from MIT and Princeton who we collaborate with to test also the absorption of water from the air and deliver for potable water purposes, because one of the most important things in a lot of hot humid climates, even, you can think about Mumbai as a great example where you have rain crashing down for 3 months out of the air, but for the other 9 months, it's not coming down, it's hanging in the air. So in many, many water stressed areas in the world, we have a lot of water ambient, and we need to figure out how to viably and sustainably collect that. Where does the water go into, and how does it interface with other things like energy? In this case, this is also a next generation system that I'll show in a larger complex that is looking at dramatically increasing the amount of solar energy in order to deliver both combined heat and power, because in built environment, we need heat for all sorts of things, but we usually need it in concentrated forms, like hot water for showering or cleaning, or heat for cooking, sometimes heat for heating in New York City, for example. But in a tight construction like this, a biomaterials construction, you would really minimize the amount of heating and cooling that you need. And so you mostly are going to use that heat for your different systems. But this is an example of a synergistic ecosystem where the first value you can see here for the solar facade is not electricity, it's not power, it's not heat, high quality heat, it's actually daylighting. Let's keep light as light because that's the highest value for both the energy and the the health and well-being of occupants. The reason why we don't often use daylighting, and this is a good example, is daylighting is never really coming into our building often in the direction, in the amount, the intensity, or the angle that we need it oftentimes, especially in commercial buildings. That's why you often will pull your blinds, turn on the lights, even though you have a ton of available energy and available light. So that system is doing all sorts of things to diffuse the light, to control how much is coming in, to control the solar heat gain. So in that case, you're both controlling solar heat gain, you're controlling the lighting loads, you're delivering way more combined heat and power than you would normally have in a conventional system. And the most important thing about that system is it's designed for disassembly and reassembly. But we'll show you in a minute why that's still a problem. This is just a quick snapshot, and we might be able to get to this at the end of this talk about how we look at things in a multi-scalar fashion, how we're looking at integration of like basically following the photons and the electrons around the room. But for those of the engineers in the room, basically what we're doing in built environment in order to get to on-site net zero, and this is net positive, obviously, for energy. In that case, they only needed 2 kW. They had 3 kW, so they could do extra things with the energy. I forgot to mention though that you can see it in that second image. There's farm walls on the outside, so there's a lot of those farm walls are for pre-filtration. They're for growing food, and they're for also controlling the thermal conditions, the cooling loads. So so plant-based starts like in the pre-filtration of water, for example, with exterior farm walls, et cetera. And so there's this whole synergy between all of the different things. And once again, I think what's hard is that I think a lot of people will look at a house and they'll say, that's a solution. You know, they want to grab onto, now we can do it like this. But what I want to offer to you guys is when we're looking at built ecologies and when we're thinking about these things as research, that's why we say open architecture. These are means for investigating potentials and means for new means for understanding. Sorry, this is not new means for understanding the interface between all of these different things, and that those just happen to be some technologies, but you could swap them in for just-in-time technologies or compare them and contrast them and almost put things into kind of play, which doesn't happen in industry and rarely, unfortunately, happens in research, academic research as well, because people choose horses and then they tend to want to defend the horses or follow the horses. What we're basically doing is allowing for several silos, several horses to be in play simultaneously. And we try as much as we can to be agnostic, even with our own systems that we're developing. And I think that that's a really, really important thing is can we acknowledge, for example, that our built environments are all experiments. And you guys know this with this building, but every single building is an experiment. Every single building is new and it is different from what has come before technically. And so if we can accept that, acknowledge it, and then as a society, really be sort of open about in the discourse about that, then I think that we will be able to accelerate innovation in the built environment much faster. And once again, I always come back to where people are sitting, because I think that this building is a good example. I've heard a lot of complaints about this building, and there's been, good reasons to complain. But I also want to just, ask you guys to really engage in evolution and in because I think when a complaint should not end with just we'll try our best or we'll fix some widget or whatever. It should come with an evaluation, a social evaluation of how things might be done differently, because as I said, this building with just a few tweaks could be operating very, very differently. So just another site for ELN, Ecological Living Network, just to show how different, let's say, things might be if we were building in a different environment. This is not a house, it's a pavilion that in this case, it's printed from post-agricultural byproducts. In this case, soy and bamboo. At the time, it was the largest, and that sort of netted structure is actually carbon fiber, but we were investigating how we might be able to transition to biomaterials for the scaffolding of systems, both solar and grown, and also how we might be using 3D printing in order to deliver very strong and sustainable structures from so-called waste streams. On the right-hand side, you can see coconut coir. These are very, very low-cost press panels from coconut waste, also soy and with soy binders in that case. And just, you know, a note about this is in this pavilion, we have many, many partners with many different byproduct streams, rice husk, coconut coir, as I've mentioned, bamboo, forest detritus, mycelia, which is also a binding material that we put in a lot of our experiments. But what we're, in this case, we were collaborating, as it says, with Oak Ridge National Labs, Shop Architects, and Branch Technologies is an industrial partner. But for the environmental control systems, one of the things we were doing is, in this case, looking at in completely open environments, could you transfer solar energy, you know, from where you're collecting it into different surfaces at will? So, for example, our colleague from University of Nairobi here is sitting on a chair that is, or a bench that can change from heat to cool through thermoelectrics at will within the biomaterials. So there's also a lot of, you know, sort of, you know, low tech, high tech things that we're putting together. But one of the things that we were interested in with this project was to see, could you, for example, completely change the game in terms of the cost of materials and where materials come from, because how we basically, and we had a lot of fun with all the students. These are our students from YSE with Kenyatta and University of Nairobi and Uganda and Rwanda. And we were looking at, could you give farmers a kind of high value added product right on the side of a farm, as opposed to what we have in built environment, which is that materials and products are extremely expensive if they take time, if they take space in a factory, if they're shipped, for example, great distances. And so that sort of throughput material economy, where we bean count both the energy, the labor, and the time and the space, and those are all costs of the system, are basically inverted when you think about a farm, where you might have a lot of time, you might have a lot of space, and you might have a lot of energy coming in if you can viably capture it and transfer it in the form of solar or wind. So thinking about these completely differently in terms of how we upcycle, so-called upcycle, people are not super fond of that that term, but we do like that term, because we feel once again that many of those waste streams that we're working with our partners are, you know, they're burnt largely. And what ends up happening is that all of that particulate matter goes into the air and goes into the water and comes back down, and it creates sort of catastrophic air and water quality problems locally. Sometimes when it's not burnt in time, it creates really terrible biohazards. So this is also an example. Invite all of you to come and visit us at the School of Architecture. This is inside Beam Lab. As I said, we don't have our YSE major lab yet, but this is a small space where we have kind of a pop-up, if you will, of an immersive lab. And why do we like to work in immersion in architecture? Because when we are collaborating, we collaborate with large international teams. We like to visit each other. So right now, that top middle part is a site in Nairobi. Some of the other slides are of a site in North Adams, Massachusetts. And what we were doing is we were sort of convening farmers and industrial producers from upstate New York and Massachusetts with farmers in East Africa, and a lot of university academics as well, and the KEFRI, the Institute for Forestry in Kenya, to sort of come together to brainstorm different methods and different means and methods for upcycling. You know, and most of the waste in upstate New York is sort of corn or hemp based or otherwise, and they have very different species, but there was so much to learn together. And that's where we like to really sort of, you know, when you're in immersive space and you're collaborating with your colleagues, they're surrounding you as opposed to being on a screen. And then especially if you're designing for a site, to be able to go and inhabit that site when you don't, especially you can think about the pandemic, but in general, it's extremely carbon intensive to have to fly so we're investigating ways, can we really be together in one room without having to get on an airplane? And so looking at those small scale instances, I'd like to just sort of scale up for a bit. A lot of times, as I said, what we're doing is we're linking so that lab scale, the small lab scale, with maybe room scale like ELN, because it's really usually just one room, it's quite small. And then sometimes there are things that you really have to investigate and develop at district scale. So I'm going to use this one as an example, but please go onto our website to look at a lot of the different projects that we've done over the years. One is the first on-site net zero school. It was the first one in the Northeast, PS 62 in Staten Island. So as an example, this building tried to be on-site net zero here. And so all the challenges you will know will be very similar, for example, on Staten Island. But I'm showing you this project because I think this project is much better than anything we've been able to do here in this country or in other places in the world. And I think once again, it's because it's really aligning all of those stakeholders that I showed earlier in the process, where there's tremendous discussion about what is sort of intended. And a much more expansive time frame in which, for example, our clients, in this case, it was the public sector in Botswana, saw the site. So this is, I had mentioned that in the context of New York or other very built up places, New Haven could be an example, we mostly have to start thinking about retrofit or start to think about how could our older buildings become net producers of biodiversity, become on-site net zero very, very hard because these are massive SUV buildings, right? They're not designed to interface with local energy flows. But if we were going to start from scratch on a site that did not have a grid, let's say, prior, was not built up, how would we think about that site very, very differently? And this is where our clients really, really led the way and were more ambitious than any of the consultants or designers dreamt to be. For example, they said you cannot cut down any of the old growth trees on the site. And so what they did by saying that is they forced the architects and the engineers to design around so this is a large an innovation hub. So just like you can imagine these big tech campuses, they're extremely energy intensive and they're also very, very deep floor plates. So what they forced basically the designers, engineers and architects to really shrink that floor plate to be as narrow, for example, as this building. Well, this is not by accident that this is a width, this room is the width that it is, because if you were any different in the shape of this room and the distance across, you would not be able to have cross ventilation, right? So we have certain rules of thumb, I'm saying without fan assistance or mechanical assistance. So if we want to actually interface with the flora and fauna and allow flora and fauna to go across the site, to cover the site, to cohabit or coexist on that site, and if we want to procure our energy and our water from a kind of at least regional, but if not, sorry, local, regional, or immediate place. In this case, it's quite an arid savanna. It's a temperate arid climate. Then we have to be very, very careful about the morphology at all scales. We cannot have these huge deep floor plates that you see in big lab buildings, like the one that's just next door, because that will never be sustainable in terms of being on-site net zero. You're going to have to power that from exterior means. And we can see here that impacts everything. You know, obviously we have cars, but where do we put them? How do we collect the water? Where does it go? How does it get recircled? The engineers and architects call this the energy and water blanket, where they were sort of intensifying bioretention. They were intensifying places for flora and fauna to inhabit across the length. Not perfect, I can say for sure. And probably many of you who really understand the habitats of these species will know that, you know, we're definitely not, you know, leaving the site untouched. But is there an attempt and is there a movement towards really thinking about not just the humans on the site, but thinking about the extended ecosystems that would go into the site? And I just want to have a shout out here about two systems. I'm going to do a deep dive to show you what we mean by whole building life cycle and thinking about the whole thing with two different systems, one materials and the other one in solar energy. So one of the innovations for this building, for example, is that that they attempted a system, probably for the first time in this case. Could you drive through renewable clean energy means right on site a factory? In this case, we would want to be far more sort of renewable energy, and we would also want to capture and sequester that carbon to put back into the cement. So we would use less cement and make it more, make it stronger. But those are all technologies that are evolving. But what's really, really important about this is when they're designing these slabs, they're thinking both about the amount of material they're using. They're thinking about how are all the environmental flows going through those materials. So they're using far less energy, concrete and steel. And then they're also thinking about what is the end of life. So they're designing for disassembly and reassembly right here. One other quick thing I'll show you is, if you can see in the distance, are there all these clerestories, windows that are popping up, facing north in this case, because we're in the southern hemisphere. That is exactly the same system that you saw in the YSE solar facade. If you think about large scale buildings like this, and if we're using these large sheds, for example, to collect energy, we're literally starting to talk about district scale power. We're talking about very, very large things. And just to wrap up on this relationship between embodied and operational energy, as I said, that facade system is much more powerful. It has the potential to be over 70% combined heat and power, as opposed to conventional solar, which is 14 to 25%, and then you lose the rest of that energy that lingers around the building as waste heat, right? So driving up your cooling loads and really not being helpful. That's an amazing number to try and get to combined heat and power 70% and reduce the lighting loads or reduce the cooling loads. But if we look at it from an embodied energy perspective, per this article in a Journal of Industrial Ecology, that very same system takes way too long to pay back the energy, the embodied energy that's in that, the aluminum, the steel, semiconductor, whatever, even though it's using less than 1% semiconductor in comparison to conventional solar. So it's way better life cycle than conventional solar, but it's still not good enough. So the point is that we need to transition. Even if we're going to look at, a very, very high performing system, we've got to transition it to biocompatible and bio-based materials. Now, I didn't have time to look at one of our systems in the Bronx, New York, but if you have chance, take a look at also just down the road where we leverage buildings as basically large scale experiments. And this is the Public Safety Answering Center in Bronx, New York. And of course, I'm putting up this, this title ironically. Safest building in what way? Because this is meant to protect New Yorkers, but in case of a bioterror attack, a Fukushima, 9/11, any of these things, you have to close off the perimeter from all air intake, and inhabitants can only last for 7 to 10 days. So what we use, we certainly don't think this is a very safe building. We use this building, for example, to experiment, and this is a large university network, including NYU, City College, Cornell, Cornell, Yale, obviously, and RPI. So it's greater capital district, looking at this building in terms of that closed loop, just to investigate what is that relationship between oxygen, CO2, the reformation of VOCs molecules or other things that we do that's what we have to take care of to deliver safe air quality. So it's basically a large scale experiment. Why do we have to do it at large scale? Because basically, there are some things that you can understand at the very large scale, but there are other things that you absolutely have to start to investigate at full scale. Ecosystems and airflow and air quality is definitely one of them. So this is just, maybe I'll just end on this slide, which is a favorite slide of mine because I just love seeing all of the interdisciplinarity. This is, as I said, many universities, but just here we have people from environmental law, cardiology, microbiology, aerosols chemistry, that's it for that slide. But there's, you have a lot of people coming around to say, how should we build in the future? What will be our interface with natural systems in the future? Could we get rid of our contemporary HVACs and actually work with plant-based means to deliver healthy, biodiverse microbiomes in the built environment, for example, in this case? So with that, I'll just end it, and please come and see us at the School of Architecture and check out our website, because we would love to have more School of Forestry students and interface with more students in this school. Thanks so much. Sorry. School of Environment. So I'm sorry I went a little bit over. I see it's almost noon. If anyone has any questions in the School of the Environment, I apologize. That was a faux pas. If anyone has any questions, please stay and I will be very happy to answer them.